Okay, so here's the second problem. I've drawn the diagram. We have a rod, and at the midpoint of the rod we have a cable attached to it, and this cable has a certain tension in it. The rod itself has some weight. The mass of the rod is this thing here, the small case m, and there is a mass attached to the end of the rod, which we're denoting by uppercase M, right? So this angle here is theta, which is 58 degrees, and L is the length of the whole rod. And since the cable is attached to the midpoint of the rod, this length here would be L by 2. The whole length is L, and the half of which would be L by 2 where the string is attached or the cable is attached. We're going to use the same principle. We know that a system is in equilibrium, so the sum of torque would be 0. There are three forces acting on the system. The first one is the weight due to this mass. The second one is the weight of the rod itself. And the third one, which balances these two, is the tension in the cable or the string, right? So we can say that the sum of torques is 0, or we could say that the clockwise torque is equal to the anti-clockwise torque. To find the clockwise torque, if we take the tension to be the clockwise torque, the torque due to these two forces would be the anti-clockwise torque. So for the clockwise torque, we have the force, which is the tension, times the moment arm, which is the cosine of L by 2, this length, right? This length is L by 2, and the moment arm is the cosine of L by 2, right? So this is the torque, clockwise torque. For the anti-clockwise torque, we have these two forces. The first one is just mg and the sine component of L by 2. This is L by 2. This is the sine component of L by 2. And then we have the torque due to this mass here. This is just mg times, this is the force mg, the weight, and L sine theta. Sine theta is the moment arm. Here it was L by 2, here it was also L by 2, but here it's L because the moment arm extends all the way to the edge, right? So just a little bit of manipulation here, and we end up with this equation. We know everything in this equation except for the tension, so we just plug in the values, and this is the tension we get, right? It's important to note that the tension, the final answer is dependent on what value of G you take. If I take G to be 9.8, it would be this thing. If I take G to be 9.81, it would be something like 6547. Or if I take G equals to 10, it would be 65, 60 or something. So it's important to check which value of G you're using, especially if you have to submit the final answer online, right? Maybe that's the discrepancy you were experiencing. Okay, so this is the last problem. We're given a rod with a mass M and a length L, right? We're given this angle theta, and this rod is attached to the wall by some cable or some string which has some tension T in it. We also know that the angle at which the cable attaches to the end of the rod is exactly 90 degrees. Okay, so we're going to use the same principle. We know that the sum of torques would be 0 since the system is in equilibrium. The anticlockwise torque due to this tension would just be the tension times the moment arm, which is L, and this torque is balanced by the torque due to the weight of the rod, which is just mg, and the moment arm is just L by 2 cos of theta. Theta is this angle here, right? So we know all the quantities in this equation except for t. So we find t to be almost 120, right? So we are supposed to find the horizontal component of the tension, right? So the horizontal component would simply be tension times the sine of theta. We already know theta, so t sine of theta would just be this tension times sine of theta, and we get this answer. Okay, this is in Newton. Okay.